So this is a cute story that just came out in Nature Communications, led by Kong Gao, and you should be careful when I say it's a cute story because I'm a co-author on it, but nonetheless it's a nice new result which belongs in this new findings of cyclones in our tropical cyclone course. The story is very simple, as you know. If you don't know, you should look up other podcasts on El Nino. During an El Nino, the western Pacific warm pool expands eastward and the region with temperatures warmer than 28 degrees centigrade become much larger in the central northwestern Pacific, and this you would think intuitively would favor more cyclones because warmer temperatures will favor cyclogenesis given the other conditions like vorticity, vertical shear being favorable, and mid-level moisture loading, and so on and so forth. So far, there have been studies showing that in fact the number of stronger cyclones can be larger during an El Nino, but the fact that the frequency of cyclones remains almost the same from La Nina to neutral to El Nino years hasn't been explained for the northwestern and north central Pacific, which is the focus here. So if you just start by looking at the oceanic Niño index, which is the average sea surface temperature anomaly in the central eastern box, which gives you a sense of the strength of the El Nino and the La Nina, or whether you are in a neutral phase, you can see that the centroid of the warm pool, which is the centroid of the 28 degree C region, varies almost linearly with the oceanic Niño index, with the warm pool being pushed far westward, west of the dateline to 175 degree east here, for example, or even to sometimes 165 degree east, or closer to there during a La Nina when trade winds are stronger, upwelling is stronger in the east central Pacific, and warm waters are pushed west. During neutral years it spread over a range of longitudes, but during La Nina it clearly expands eastward, going well east of the dateline to 165 degree west. Okay, so if you look at the tropical cyclogenesis number, on the other hand, it has basically no correlation with the oceanic Niño index, whether it's a La Nina, neutral year, or an El Nino year. Cyclogenesis numbers range from 0 to over 8 or so, and in fact the highest number here is during neutral year as well. What causes this? That's the main story, that's the main new result. If you look at the joint distribution of tropical cyclogenesis numbers with respect to the mean upper ocean mixed layer temperature, mixed layer is defined as the depth where the surface temperature drops by 0.2 degrees C, so that's the region where wind mixing, heating, cooling can create turbulently mixed vertically homogeneous layer. So if you look at the cyclogenesis number, obviously they occur when the temperatures are warm enough and when the heat content or the cyclone potential increases as measured by the depth of the 26 degree isotherm in meters. You can see that for the same temperature, if you increase the heat potential, the hurricane potential or 26 degree isotherm depth, then the cyclogenesis tends to go up, especially when temperatures are in the 29 to 30 degree bin. And of course there is an optimal temperature beyond which the cyclone potential drops again, but let's not go into the details there because it depends also on what's happening with the vertical shear, vorticity, moisture loading, and so on and so forth. Keeping that in mind, you look at the Genesis Potential Index Ocean. There are several Genesis potential indices defined by different authors depending on what they believe is critical for the conditions that have to be met for cyclogenesis to happen. This one, what's new about this is that it includes an oceanic parameter of D26, and it's argued here that that is critical for understanding why the frequency of cyclogenesis doesn't go up during an El Nino. So the parameters considered here: the absolute total vorticity at the surface, 1000 hectopascal. This is relative plus planetary vorticity with an exponent. The exponents F, G, H, and I here are fixed numbers derived from observations, so empirically derived, and it depends on the mixed layer temperature T bar and also on the long wave radiation from the surface, which of course is T to the fourth, but it also can affect the so-called Carnot cycle framework for the cyclogenesis, where you are moving heat from the warm ocean to the cold upper atmosphere. And D26 of course is our hurricane potential. What we want to do is to see if there is a sensitivity of the GPI ocean to various changes in temperature, long wave, and D26 and vorticity. So that's the standard chain rule, where you say we want to look for the sensitivity of delta GPI, then you look at the gradient del GPI with respect to the vorticity, you hold other things constant and look at change in vorticity as delta eta 1000. Similarly, with respect to temperature, hold other things constant with respect to long wave and with respect to D26. This gives you a sense of who is controlling what in the tropical central and western North Pacific when it comes to cyclogenesis during an El Nino compared to a La Nina. So this is the tropical cyclogenesis numbers during El Nino and La Nina and their differences. So these are done with two GPIs. The one that doesn't consider the ocean and the other one that does. But you can see that the message is still the same: El Nino, La Nina, and the difference. During El Nino, generally there are cyclones being born much further east compared to La Nina, but the difference shows that there is more cyclogenesis potential as computed in this region, and it's reduced here. So it's positive here, increased during El Nino, decreased during El Nino. So the overall numbers remain the same. So the critical thing is to understand why, even though there is favorable conditions for cyclogenesis potential here, the total number of cyclones don't go up during El Nino. So we'll see that this is also true in observations. These are the number of cyclones from Joint Typhoon Warning Center for El Nino, La Nina, again born further west, which means if they travel all the way here and survive, they have time to get stronger, even though it's not always clear that how long they travel has anything to do with the intensity. Nonetheless, you can see that compared to La Nina, there is generally a decrease, or there is a decrease here in the cyclogenesis number, and the overall numbers remain similar to a La Nina. So that shows here also in terms of the difference of the cyclogenesis. This is from observations, generally negative here, generally positive there. Okay, so if you look at the differences in the upper mixed layer temperatures, during an El Nino, there are colder anomalies here because the warm pool has moved east, convection has reduced here, temperatures have become colder compared to neutral years, and so on. So warmer temperatures do occur. If you look at D26 between El Nino and La Nina, on the other hand, they are negative generally over both of these boxes. This is the tropical northwestern box, and this is the north central box. And if you look at the sensitivity of the Genesis potential index to temperature, it's positive here, which means temperatures are warmer and they favor increased cyclone genesis. But when you look at the sensitivity to D26, both boxes are negative, which means reduced heat content is actually disfavoring cyclone genesis in so the difference in GPI is negative in both of these boxes when you compare El Nino and La Nina. That's the main message. And then you can look at some details. Opposite correlations between the upper mixed layer T bar and 26-degree isotherm D26 in the tropical northwestern Pacific and tropical central North Pacific. So here is the correlation coefficient between T bar and D26 during all months which are chosen for El Nino and La Nina. So the flavor of El Nino, Central Pacific El Nino, Eastern Pacific El Nino, doesn't make any difference here because the wind response in this region and the SST responses are similar for both all flavors of El Nino. So you can see here that correlation coefficient is negative here and it's positive here. So cold SSTs here come with shallower D26, but surprisingly here, warmer sea surface temperatures are associated with shallower D26. This is a critical message. So if you look at the D26 anomaly and T-bar anomaly in this box, during El Nino, there is colder anomalies here and shallower D26, so they are in this range, and during La Nina this region is warmer, so you have deeper D26 and warmer T-bar anomalies. Whereas if you look at this box, you have during La Nina colder T-bar anomalies and deeper D26, whereas during an El Nino you have much more of positive anomalies and negative D26 anomalies. Okay, it all makes sense. During La Nina you have stronger trades upwelling in the east, pushed warm waters deeper, thermocline D26 in the west, so you have La Nina colder and deeper D26. El Nino is discharged, winds change in a way that D26 is lifted, as we see in a minute, but the temperatures are warmer because the warm pool has expanded into this region. You can look at this in terms of vertical profile as well. Blue area is showing basically the reduced heat content during El Nino because the D26 is shallower. So this is for the western box. You can see that the profile is on average shallower, so during La Nina it's deeper. So compared to La Nina, El Nino has reduced heat content, and this has the similar profile here. Even though near the surface heat content changes are much smaller, albeit a little positive, but it turns out that this region is highly affected by the anti-correlation between D26 and T-bar, which constrains the cyclogenesis in this region, which is what gives us overall a similar number of cyclones during El Nino despite the expanded area of warmer waters. So these are basically showing the winds and the wind curl anomalies. Positive anomalies means Ekman pumping and upwelling, and we don't care about this region. So you can see that the Ekman pumping generally positive over here, more so over here. Wind stress curls are stronger, and you can look at that in terms of upwelling velocity and D26. As you expect, upwelling velocity negative means convergence, and you get shallower D26 anomalies. Let me make sure we got this right. The see scatter plot of regional mean, wind stress curl anomalies and D26 anomalies in the tropical northwestern Pacific. So these are the positive curl and negative curl. So the western box has a negative correlation of -0.68, whereas the eastern box here, the solid box, has a much higher negative correlation between upwelling velocities and D26 anomaly. So the wind stress curl impact here is much larger, and this negative correlation is very unlike what we expect. Okay, so you have upwelling anomalies, deeper D26 during La Nina and shallower D26 during El Nino. Remember, in the east all the El Nino theories want a positive correlation between SST and D20. When the D20 gets deeper, SSTs get warmer. This is what gives us positive feedback between winds, SSTs, east-west gradient, thermocline, and Birkness feedback, whereas in the west it's got an anti-correlation, which is not something intuitive, so it would have been missed thus far in terms of how the north central Pacific box is constrained by this anti-correlation between surface temperatures and D26. So the sloshing of the warm pool brings warm waters, but wind stress curls lift the D26 and reduce the heat content. So overall cyclogenesis potential is favorable, but actually number of cyclones born do not increase because of this reduced heat content. Okay, this story will be investigated it further, I'm sure, but for now this is a nice new result that for the first time explains why the cyclone frequency doesn't change from La Nina to El Nino in the northwestern and north central Pacific region. Okay, let's leave this here for now.